So today we are going to discuss the YDC in which we use single source and a mirror so that the reflection can create the virtual source and then it will behave as the double slit experiment. So it was performed by a very famous scientist called LIyod. This is called LIyod's single mirror method. So what we do in this method, we take a mirror and technically very close to mirror and certain distance away, we place a source. Okay. So our source is going to be somewhere very close, millimeter above this plane and less than millimeter, you can say. But for the sake of drawing, I'll draw it here. Okay. So this is your position of source. So let's say this is L, or you can say B, A, B, C is also fine. A, B. And the screen on which we are going to obtain the interference pattern is somewhere here. And this distance is, let's call C. Now interference means at least light should come through two sources, but here we have only one source. So we need at least two paths, like light ray should travel two paths so that there should be some path difference and then only we can have the pattern, right?
Yes.
So this is your screen. Now light can travel from the source to the screen in two ways. One is direct. So light can directly reach here, here, here. It can reach here also, here also, here also, here also. But the moment you make that, hit the mirror, but the moment you hit the mirror, the light cannot go below, rather it will reflect from here and will reach some point here, right? Something
Yes,
like that. So the reflected light can reach this point, and this is the nearest to the center of the screen. The farthest that it can go is if it will hit the mirror near this edge. So if you hit at this edge, what will happen?
sir. It will get reflected to the highest point available.
Correct. So I think this is. So one thing is clear that the reflected light can reach up to a portion which we can show it here. This is the region in which the reflected light can reach actually.
Yes, sir.
And direct light can reach anywhere above and up to certain distance below, right?
Yes, sir.
So if I just take the edge, if the light is slightly off the edge, it will be he's coming somewhere here, right? Just so the direct light can reach up to this point. If it is slightly off the edge, isn't it?
Yes, sir.
So now the one thing is clear that light can reach through reflection up to this region and direct light can reach anywhere above this point, right?
Yes, sir. Sir, the A region is solid, like solid ground.
Pardon, which one? A no, A is uh, open space. So okay, you mean to say it can reach below, right?
Yes, sir.
Yeah, it can go anywhere here. Yeah, correct. So this light will never interfere with the reflected light, right?
Yes, sir.
So we are looking for the region in which the reflected light can meet the direct light,
Okay, sir.
because otherwise there is no question of interference. So who will this interfere with?
No one.
Yeah, no one. That's why this light is of no use. So we only look for the reflected part because see, wherever the reflected light can reach, in this case, direct light can reach for sure.
Yes, sir.
And other reason we are not interested. So this reason, I'll just do differently. So this region is called region of interference. And we are particularly interested in that region itself. No other answer. Okay.
Yes, sir.
Okay. So if I call this as theta, this is also theta. If I call this as theta dash, this is also theta dash. Right?
Yes, sir.
So I would like to find the length of the region of interference, which is geometrically possible to be calculated using trigonometry. So this height you can get easily, and you can also get this height easily. Then we can take the difference, we'll get the answer, right? So let's call this as y1, this is called y2. So we have y1 and y2. And we can add tan theta equals to, so on the right of the triangle, the tan theta is y1 by c, right?
Yes, sir.
But on the left, what we have? On the left
Sir.
of the same triangle, it is h by a plus b.
Yes, sir.
So we got y1 equals to ch upon a plus b, correct?
Yes, sir.
Similarly, tan of theta dash, if you want to write on the right side, the right triangle, it is y2 upon b plus c, right?
Yes, sir.
But on the left, it is h by a.
Yes, sir.
So y2 becomes b plus c into h by a, correct?
Yes, sir.
So a region of interference is y2 minus y1, isn't it? And it turns out to be b plus c upon A minus C upon A plus B or into H. So definitely the first term is bigger than the second term without any doubt.
Yes, sir.
Okay. Now in the LIyod mirror method that we actually employ, we make C almost 0. So if C tending to 0, that's very interesting. So equation 1. Okay, I'm writing here. Oh, I can actually. If C tending to 0, so if the screen is next to mirror itself, so we have to assume tending to 0, we cannot say 0 exactly. So in that case, what will happen? Let's call delta y. So the region of interference will be how much? B by A minus C by A, 0 only.
Yes, sir.
Into H, which is BH by A, isn't it?
Yes, sir.
Okay. So every light which is getting reflected from the mirror, we can think that light as coming from some virtual source, right? So if you trace this blue light, if you trace the blue light backward, so it seems to be coming from, just a moment, this virtual source S dash. Okay. And by the property of reflection, this is also going to be theta dash. So this is also going to be H, isn't it?
Yes, sir.
So instead of taking the reflected light and direct light as a two source, we can take S and S dash as a two source, and we can think of interference due to these two source, but only for the region of interference, not everywhere else, isn't it?
Yes, sir.
So this is the first geometrical part which you need to know, that how we convert a question into YDAC. So now the moment you take the S dash as the virtual source, and if you want to compare with the the regular YDAC, so the YDSC equivalent so YDSC equivalent will be how much? The small d becomes 2h, and the capital D becomes A plus B plus C.
Yes, sir.
And once we have done this, we can leave this entire thing, and then we can go on solving the condition for maximum and minimum. But there is a catch here. The blue light is suffering the reflection. So
Yes.
any light which suffers reflection will have the phase shift. So the phase will change by pi actually, or you can say wavelength will change by lambda by 2. Path reference will change by lambda by 2. So
Yes, sir.
any light that we consider coming from the S dash, any light that we consider coming from the S dash will contain extra length of lambda by 2, even though it is geometrically equal, but we have to consider lambda by 2 extra. Why? Because of the reflection, because that is coming through reflection. So the point to be noted here is, due to reflection, phase will shift by pi. So what we'll do, in solving question, we will take that path as lambda by 2 extra. So for every reflected light, you can add lambda by 2. That's a thumb rule. You can always proceed that way, or you can subtract also, but it is always good to use the addition. Okay.
Yes, sir.
Now the question is how to solve the condition for maxima and minima. So in this case, you can again draw the equivalent YDSC in which we have only S and S dash. We don't have the S1, S2, we have S and S dash. The D becomes 2H. You just do the line of symmetry. Draw the mirror. Okay. And
Yes,
once
sir.
we have done this, then the same rule. You can draw like this. Let's say this is the point of interference P. O. And we are assuming that this point of interference is lying in the region of interference. Okay. So this is the YN. Now the S dash P, the way we solve is we take S dash P by adding lambda by 2 extra. So even the P point will look like this. This is lambda by 2 extra. Okay.
Yes,
And
sir.
therefore, even if you are at the origin of the screen, if you are at the center of the screen, just a moment. These paths are not equal. So this path is actually lambda by 2 extra.
Yes, sir.
And that is why the interference at O, okay,
Yes, sir.
interference at O, okay, now in our case, O cannot have the interference at all. Why? Because the region of interference starts somewhere here.
All right. Yes, sir.
So the interference will only happen beyond that point. So at O, there is no interference, in fact. But the point O can be a point of interference under a situation when C becomes 0. Because as you make C 0, Y1 becomes 0. The Y1 becomes 0, right?
Yes, sir.
So in that case only, the O will have the O will fall into the point of the region of interference. But nevertheless, the process, let's talk about the process, how we solve question. So we write the optical path difference. So the delta X, just the geometrical path difference is how much?
Sir,
S
where
dash P minus
exactly?
SP.
Yes.
But with the moment I say optical path difference, the answer will be S dash P plus lambda by 2 minus SP. Understood?
Yes, sir.
Because the reflected light will suffer a phase shift of pi, which means the path difference equivalent of pi is lambda by 2, right?
Yes, sir.
And if medium will come, then that will be considered separately. So we are not considering the medium change. We are still considering that it's air only. So the way of writing will change. It is S dash P lambda by 2 plus minus SP. Okay. So
Yes, sir.
we are not supposed to use this. So we always use this relation for the condition for maxima and minima. So for maxima, we can write delta X OPD equals to N lambda, correct?
Yes, sir.
So S dash P plus lambda by 2. Okay, okay, let me tell you that S dash P minus SP, and S dash P minus SP is always D sin theta, right?
Yes, sir.
This is basically D sin theta plus lambda by 2. Okay.
Yes,
So
sir.
we can make this slightly easy to write now. So we can add D sin theta plus so what you can see that the if you only look up for the geometrical path reference, it looks like the condition for maxima has converted into condition for minima. So it is now the odd multiple of half wavelength, right?
Yes, sir.
Because this is anyway lambda by 2 bigger. So the first maxima will occur when the geometrical difference is lambda by 2 itself. Because if this is lambda by 2, then this will add up to lambda.
Yes, sir.
So if geometrically d sin theta is lambda by 2, you will get the maxima, isn't it? The first maxima.
Yes.
Provided that first maxima is beyond the y1, so that is a region of interference. Okay.
Yes, sir.
Now that's why the y1 creates a lot of disturbance in solving questions. So what they do is, in most of the questions they don't take c, they make c tending to 0. Okay. So
Yes.
for c tending to 0, if we solve, then we can remove y1, right?
Yes, sir.
And in that case, the y becomes the central minima. Which means near O you will see a darkness. Do you realize this? Yes or no?
Yes, sir. It will be a minimum.
Yeah. It is like the mirror has come almost here. This is the middle part. This is A part. So let me do something like this. So the point O is the point of minima. Okay.
Yes, sir.
It is clear?
Yes, sir.
Okay. Let's do. Okay. So now the rule will just flip actually. So the condition for maxima becomes condition for minima. The central bright fringe will become central dark fringe, and the region of interference remain easy. So we can say the delta y, which we call the region of interference, that will be equals to y2, right?
Yes, sir.
So we can say y2 and so y1, but that will become how much? How much? It was bh by, right? It was bh by. Yeah. Okay, but now we know that the fringe width formula in from YDC experiment. So the condition has changed. That's fine. So we can say dyn by capital D is 2n minus 1 lambda by 2. So the position of maxima, you can write position of maxima dy1 by d is 2n minus 1 into lambda by 2. So the yn comes out to be how much?
D by D.
And we can write as 2n minus 1 lambda a plus b by 4h, right?
Yes, sir.
D is 2h, so yn is 4h. Similarly, condition for minima will be d sine theta plus lambda by 2 equals to 2n plus 1, or I can write like this. N plus half. No, like this. Yeah, that's fine. N plus half into lambda, right? This is how we write 2n plus 1 lambda by 2.
Yes, sir.
And what you can see that this half will cancel out. So the d
Yes, sir.
sine theta becomes n lambda. So you can see the role has been reversed, right?
Yes, sir.
Now, when you see a formula in which we have 2n minus 1, the n will start from 1. Because n, if you put n equals to 0, it will give you negative answer, which is it means it's below, but that's okay. So we just consider n equals to 1, 2, and if it is positive, then we take n 0 onwards, right?
Yes, sir.
Okay. So now you can see n equals to 0, we can put here. So 0 order, if you put n equals to 0, you can see we have 0 order minima. Because geometrically, the point of arrival, if O is the point of arrival, then it is equivalent in terms of length. But the reflection is making the one of them to flip actually. So instead of meeting in the same direction, they are meeting in the opposite direction, in which in turn is cancelling the effect. Understood?
Yes, sir.
So if the amplitude of the first wave is upward, and if there is no reflection, second would have been like this, but because of the flip, they cancel each other. So in vector terminology, it is the opposite vector of the negative vector of the first vector, and therefore the addition is 0. So that is the reason for the central minimum or central darkness. Okay, central dark fringe will be obtained. Now there is one more question that you may be asked, that is called the number of fringes. The number of fringes on screen is simply the region of interference divided by fringe width. Okay. Because we cannot have the luxury of obtaining fringe everywhere. And also we cannot obtain fringe below. So because C is 0, so you know all the diagram will be above only. The light which will reflect is above the mirror. So we have only one side of fringe, other side we don't have any fringe, right?
Yes, sir.
Now, the delta y we got as BH by A, and beta is always the same formula, lambda d by d. So lambda capital D by D, capital D is, so I'll just add the formula. So capital D is A plus B and small d is 2h.
Yes, sir.
So 2b h square upon lambda A. This is the number of fringes that you can obtain on a screen for the case. So our syllabus is all about C tends to 0. Okay.
Yes, sir.
And then you can, apply this single source interference, or you can always obtain the single source interference using reflection. So a single source, if producing interference, it means it is using direct light and the reflected light for behaving as two sources. And because the reflected light is also coming from the same source, so they will maintain the coherency. So the rule of coherence will be maintained. We need not to worry about the coherency because it's coming from the same source. Okay.
Yes, sir.
But we have to make sure that the overall path traveled by the reflected light and the direct light is not differing much. So the path difference should not exceed the, if you remember, coherence length, right?
Yes, sir.
So there is a difference up to which interference can happen. If the difference is too large, it will not interfere. And that is why in our day-to-day life, if you try to obtain this, it's very difficult. So
Okay, sir.
you need to take a very thin laser light, and you have to take a mirror and you have to put the laser light beam very close to this axis somewhere here. And if you if you make it reflect from the mirror, you can see the pattern.
Yes, sir.
If you want to see, have you seen the mobile phone?
Sir?
Have you seen mobile phone? Do you have mobile phone?
Yes, sir.
So you must have seen, right?
Sir, mobile phone. Yes, sir.
Yeah. So, if you look at the screen, what you see? You see a very uniform, fine, polished glass, right?
Yes, sir.
But this glass is very unique glass. It is called a carved glass. So there is some, carving actually, which you don't see.
Oh,
So there are many layers to the glass actually. So if you hit the surface of the mobile phone with the laser light, you will see a pattern actually on a wall actually. So that is
okay.
kind of a diffraction pattern. Okay. You have
Oh,
laser light?
no, sir.
Just a moment. Oh, I realized that, okay, I have only one phone. So if I make the interference diffraction, then I cannot click the image. Okay. So what you can do is you can take any laser torch, which is available in the market. It's very cheap. And using that torch, you can always obtain the
Diffraction.
diffraction. Yeah. So you can see it very clearly. It's very common, I mean, very easily observable thing. And you can see a lot of things by using.
Sir, your voice is too low.
Okay, am I audible now?
Yes, sir.
Okay. And you can also take your hair strand and you can throw the laser light through the hair strand. And once the laser will cut through the hair strand, it will show you diffraction pattern as shown in the books. Similar.
Okay, sir.
So yeah, once I'll click those photographs, I'll send you.
Yes.
So it's very easy. I mean, easy. You can buy one. It's 300 rupees from Amazon. You can get and perform this experiment at home. You'll enjoy it. Okay. So that's all from the LIyod. I mean, we are not going to solve question because the rest is similar to the YDC. So whatever you do there for finding the first maxima, first minima, and so on, you can keep on doing like that. Okay.
Yes, sir.
What you also need to realize that a zero order maxima is not possible. So you don't put in zero. So you can see maxima is formula is 2n minus 1 lambda d by d. And n will start from the 1. So you get to the first order maxima onwards. Okay.
Yes, sir.
Next. The next is called the Fresnel's biprism. Fresnel's biprism. So in the Fresnel biprism, what we do is we take a very thin glass slab. Imagine you have a glass slab as thin as this. Can you see
Yes, sir.
how thin it is, right?
Yes, sir.
But if I do such thin, then you won't be able to understand anything. So I have to make it slightly more. In fact, this much more. Okay. So you can imagine it's the thinnest possible. And what we do next is we rub the, you can say, scratch the surface to make it something like this. So for the sake of saying we are calling it a prism, but it is like a thin slice. It's like thinnest possible slice of a maybe glass. And then you convert into prism in this shape. Okay. So now the two surfaces are not parallel, they are having some angle. Okay.
Sir, is it like a double-edged wedge?
Yeah, correct.
Okay.
So why we call biprism? Because technically you can think this as two right angle prism like this.
Okay, sir.
But we don't take the two prism, we don't take two separate prisms. We have to keep one single prism because once you cut it, the light will behave differently. The corner case will change. Okay, so generally we take only one prism. Okay.
Yes, sir.
And it is very thin. It is so thin that this is called the thinnest possible prism. And in fact, this angle, you won't believe, is roughly 0.5 degree. So you can imagine how thin is this. And it is almost like a thinnest possible slab with slight difference in the angle. 0.5 degree, you can understand how small it is. 1 degree you can see on a D, on a protector. Half of that value is the. So this is almost flat, right? Will you be able to
Yes.
see this biprism shape? Anyhow, the answer is no, because this is almost 179 degree. And we cannot distinguish that 179 is a flat surface or curved surface or bent surface. So the 1 degree bent we can't see, right?
Yes, sir.
So, okay, I'll not do this. I'll not do this also. So you can call this as angle prism A. So what I'll do is I'll do it separately. So this prism shape I'll do it separately. This we call the angle prism because the light ray will go from this and this surface. So that is also called the angle of refraction or angle of prism also. Now, because it's made of some material, some medium, it will have some refractive index. You may think the surrounding is either air or having some other medium also. So that is up to you. You can choose whatever you want to assume. So let's say the surrounding is the medium, mu m. So I'm not considering this to be air. Let's consider something other than air to make it a very general derivation. So around this prism, there is a medium, let's call mu m as the refractive index of the medium. And it is the thin prism. So what is the property of thin prism that you need to know from geometrical optics? Have you read that?
Sir,
So,
no, sir, I haven't reached this part yet.
so when a light will enter the prism, it will deviate, right?
Yes, sir.
So so this is called angle of deviation. So the incident beam and the refracted beam will differ in path, and the path will turn by the delta. Delta is called angle of deviation. And what we need to remember here, that the angle of deviation of a thin prism is constant value, and also it does not depend on the angle of incidence. Okay,
Yes, sir.
so it is simply the value given by the formula mu minus, or you can say mu upon mu medium minus 1 into A. This is the formula for deviation. If it is air, then it becomes the deviation formula becomes, in that case, mu minus this is in general. This is for air only, right? So most of the questions that you will come across will be air, but if medium will come, then don't worry. The deviation formula will change. Okay,
Yes, sir.
just so now again what we do is we use again a single source which is kept symmetrically. Okay. Okay, and now we have a screen. So the distance between screen and this prism, let's call this as B, and distance between the source and this prism is, let's call A. Okay. So anyway, these are the distances. All right.
Yes, sir.
So now what will happen? The light ray will travel from the source. Now, if you go exactly this way, then okay, exactly this way means it's difficult. Some beam will go from the above, some from below, right? Because a beam
Yes,
is a
sir.
bundle of light, right? So we don't have a single exactly single ray is not defined. So we always have a beam actually, because it will have the collection of light rays. If you are slightly above by even 0.001 degree, you are a part of the upper prism. But if you're slightly below, you are part of the lower
Lower phase.
plane. Okay.
Yes.
So what will happen if the light ray will travel in this fashion? So if the light ray will go in the upper prism, you can see deviation is below, right?
Yes, sir.
Because the rule of deviation is it always happens towards the base. So if you go above, it will try to go towards the base. Base is below, right?
Yes, sir.
So the light ray which is traveling to the upper prism will deviate like this. Do you realize this is the deviation angle
Yes, sir.
for the upper prism coming near the base? But at the same time, the light entering the lower prism will deviate upward.
Yes, sir.
Understood?
Yes, sir.
So the light ray will. So now you can see that this is the upper prism light. This is the lower prism light. Okay. Now, as usual, what we do is we extend this light ray backward.
Yes, sir.
Like this.
Sir, can you just come back in a minute?
Yeah, sure. Yeah.
Yes,
So
sir.
now we have taken the light ray close to the base. Now what will happen if we take the light ray close to the edge? So it will again deviate by the same value. Now as a method of, you can say, trick to draw the diagram correctly, we extend the first two line and exactly above the source we call a point S1 S2, and now this light ray will bend. I'll tell you how it will bend. So just to join this line like this. Okay, and this line will be like this. You can see that this lateral will also bend. This is the deviation actually, but same value. And this will also bend. Now, what you can see that you can see the two color, blue and okay, I should have used white, yellow. Let me make it yellow first. Okay. Now, what you can see that the the blue is spread from here to here, right?
Yes, sir.
But the yellow is spread here onwards, right?
Yes, sir.
Difficult to realize, isn't it? You can realize this? No?
Yes.
Very good. So you can see there is an overlapping region. So interference will happen between the light coming from the top and the bottom prism. And therefore this is called now you know what this is called. Region of interference. Okay.
Yes, sir.
So it is this region in which the light ray will interfere. Okay, like this. So the question is, what is the width of this region? Okay. So because we are taking the thin mu to be sorry, a to be very small, so you can say the delta is also going to be very small, isn't it? So
Yes, sir.
it is so small that probably we can't be able to see it. And A and B are very far away. So we can first of all we'll try to find this length. What is this distance? So you can think this is the arc of a circle of radius A, because this is A. This is called A delta. Do you realize this?
Yes, sir.
So this is called A delta, and the region of interference you can say is tan delta equals to, if I call this as width W, just a moment. Okay. So now we got the small d, now YDSC equivalent. We always look for the YDSC equivalent. So the small d becomes 2a delta. Okay. Isn't it?
Yes, sir.
And the and the capital D becomes a plus b.
Yes, sir.
Okay. Width is a separate calculation. So for W, we can directly write as 2b delta.
Yes, sir.
These are small angle approximations. So we can add 2b delta. And delta, if you want to write it in general or for the air. And let's say this is for air to make it easy. So we can write as delta air. And this will become mu minus 1 into a, right? So what will be the fringe width? Lambda d by d. So number of fringes will be W by beta, which is equals to 2b delta by lambda a plus b by 2a delta. So it is 4ab delta square by lambda plus b. You can substitute delta square as and when required. Okay. So these are the questions that will come across. There is one more experimental question which they may ask you. And let me ask that for the fund that question, sir. Just a minute. So that experiment generally, okay, I have taught in the geometry optics lecture. As you will see, you will see also in the chapter of lens, there is a concept called displacement method. Okay, so I think then I need to teach the entire thing. So better you can just see that displacement method in the lens chapter, and once you will see, you will understand this. So generally, what we do is the S1, S2, which you can see here. So in the
Okay.
examination, they will not give you the S1, S2. They will not give you maybe the delta also. Rather, they will tell you that if you perform some experiment using the convex lens, so the sharp image of S1, S2 is obtained for there are two position of lens, and from there we determine the the separation between the S1, S2. Okay, so that is quite the displacement method which I have explained. So I will say read or watch displacement method.
Sir, approx which one, sir?
That will be after the prism chapter.
Okay, sir.
Yeah. So it will take some time for you to. That's the last few chapters. Maybe last 3, 4 chapters. That's last 3, 4 lectures.
Okay, sir.
From next time I'll make the heading better, but okay. So let me just show you a simplified version. So what was So what will happen is, let's say you can just do it like this. Imagine this is your S1, S2. So in the method, what we do is we take a convex lens and we keep on moving till we get the first sharp image on the screen for the S1, S2. So we move like this. Okay. So let's say this is the first position when you obtain the first sharp image, and this happens when the distance is some value. So let's call u. This is called v, the object distance and the image distance. And there is something called magnification of lens, which we write as v by u. So in this case, because v is bigger than u, you will get a magnified image. So let's call m1 the first magnification, and the first magnification will give you an enlarged image of size. Let's call that size is d1. But if you switch the position of this mirror, this lens, such that This is like V, this is like U. So the magnification will be how much? U by V, right?
Yes, sir.
And in that case, you're going to obtain a diminished image, right? Something smaller.
Yes, sir.
So the question is, if we know the D1, if you know the D2, then can you find D? The answer is yes, we can do. Because the M1, M2 is how much? 1.
Yes, sir.
M1 is the size of the first image upon original object. M2 is size of the second upon D. So D becomes under root of. So given the size of the two images for the two different position, they will ask to find the size of the S1, S2, or you can say find the equivalent slit separation. So in that way,
Yeah.
questions are asked generally. Okay.
Okay, sir.
So now there is one more something called Fresnel double mirror method, but that is not part of JEE, so we can leave as of now. I'll mention the name. If you are interested, you can read about it. So we'll go for something called interference Okay. So imagine we have a lens. Now these are from lens chapter. Nevertheless, we will learn it. So imagine we have a lens, okay? And this is the axis of the lens, okay? So what we do is we cut the lens into two halves from here. Let's say cut from here. And then you shift slightly away from the axis. So I cannot cut and shift. What I'll do is I'll make a smart move. Just Okay, so now what we do is, okay, I have cut and I have shifted already. All right. Now, of course, you have to make the shift very, very small. So this gap is very, very small. And we call this gap as D naught. Okay. And so we again have a source here at some distance from the lens. Let's call A. So you can use the lens formula, which is so for a given U, you can find the V, the image position. Okay. So this
Yes.
V will this V will have some value which you can solve. So we keep A bigger than F to get the real image. Okay. I think A is not looking nice. You can call this as U itself. So the V turns out to be how much? Correct. This much is the answer.
Yes, sir.
Using
Sir,
tell me.
sir.
Yeah.
Sir, I have this doubt, like in in deriving the lens formula or mirror formula, we're already applying the signs during its derivation. Then why again, while solving questions, we are applying the same signs?
Yeah, that's a good question. So the reason is when you derive the formula, you derive for one particular lens, right?
Yes, sir.
But it is valid for all kind of lens, concave and convex both.
Yes, sir.
So when you derive using the symbol, okay, so we have to obtain the answer in terms of symbol. The symbol, when you apply for one particular lens to get the derivation, it will be biased answer, right? It is only meant for the that lens. So how to get rid of that lens assumption? How to get rid of the, how to make it generalized? So although we use symbol, but we use symbol with sign for the given lens. So our symbol will be preserved, right? We are not disturbing the symbol, isn't it?
Yes, sir.
So whether we derive using the concave or convex, our answer will be valid for both, because while taking the symbol, we took the sign as well. So that is making
Yes.
you free from the mirror lens or mirror used actually. Because every derivation we do, we use either convex mirror, concave mirror, convex lens, or concave lens, right? So we choose something to derive.
Yes, sir.
And every optical, you can say every optical element will have different value of focal length, a different sign of focal length, plus or minus. So symbolically, we choose symbol, and we have to understand something called value and symbol. Okay. If I ask you what is U here, so I'm taking U here as value, not as symbol. What is F here? F is value, not symbol. Okay, everything is value. But when I'm writing formula like this, what is here? These are
Symbols.
symbols. They are not values. So it is confusing that what if I choose both as same, symbol and value both as same. So when you're deriving formula, you take symbol and you treat as value because you're using for one particular lens. So you take symbol and you use value, which gives you answer for that particular lens or mirror. But because you have chosen the symbol with sign, symbol is still preserved, right?
Yes, sir.
And so when you're solving actual question, then you substitute the value only, right? Do you substitute symbol there? No,
So we do substitute the symbol.
no, only for unknown value.
So the symbol is like VUF.
F.
So it's like,
So let's say you know U. Okay.
yes,
So
sir.
what you know is called value. And what you don't know is called symbol, right? Because
So
you don't know, so you keep it symbolically as such. Okay. So how you write? 1 by V minus 1 by, what is U here symbol, which is minus U, as per my question.
yes, sir.
What is F symbol? But what is F here in my question?
Plus.
So because I don't know about V, so I'm keeping V as symbol only. So I'm getting 1 by F minus 1 by V. Understood. So my answer is how much? Now this could be positive, this could be negative. I don't know.
Yes.
So because V is a variable, so if it is positive, then V is real. On the right hand side, if this is negative, the V is virtual on the left side. Understood.
Yes, sir.
So we have to be careful with the symbol versus value. Sometimes we choose both as same. Okay. So we know that the focal length of convex lens is positive. That's why I'm putting plus F as a value.
Yes, sir.
Okay. So the good thing is that when you derive formula, you put a symbol with sign. So that is still not value. That is symbol with sign. Understood? So
Yes, sir.
symbolically, it is still symbol only. So at the end, our derivation is symbolic derivation, not the value derivation.
Okay, sir. So if it's like negative, we turn it into a value by making it as minus U, which becomes positive then.
Correct, correct.
So at the end, if we want to substitute the value to be negative, then we can make it to be negative while applying the formula.
Correct. When you apply the formula, so you have the symbolic model, skeleton actually. It's a symbolic skeleton in which you substitute the value actually. And the value which is not known to you, you leave as symbol. That's why it's very confusing. In ray optics, the only confusion is the difference between symbol and value. So every formula which you see is a symbol or symbolic formula, not a value formula.
Yes, sir.
Okay.
Got it.
Yeah.
Yes, sir.
Okay, anyway, so we have V. So now, because I'm assuming this to be real, so V will be somewhere here. Let's say if this is V somewhere here. So for this S, this is a V. So how we do it like this? So we take a light ray, leaving this edge. So the light ray which will pass through the edge will pass undeviated because that is the optical center of the lens, right? And the light which will travel at some angle will bend towards the normal, right? This is how it will happen. and same thing will happen on the other side.
Yes, sir.
And this will act as the two virtual object. So this is your virtual object. D. Okay. And the distance is how much? V. Now here the V is value actually, or you can think a symbol, but here V is value. U and V are values. Okay.
Yes.
So how? Oh my God, I got some sound. Okay. Anyway. So this D and this D naught, we need to relate. So we can relate easily by simple similar triangle. So we can say D naught upon U. Now you may be wondering why I'm taking D naught. Basically, the same source will act as object for both lens. Now there are two lens actually, upper lens and lower lens. For upper lens, the source is D naught by 2 below, right?
Yes, sir.
For lower lens, it is D naught by 2 above. Okay. So it is like the situation is something a bit complex. There are two objects. Of because the first upper lens will see the principal axis will move along with the lens itself. So as you move the lens, the principal axis will shift actually. Like this.
Sir, is it like parallel, but then it's displaced?
Yeah. This is the principal axis. Now there we have, instead of one, now we have two principal axes. One for each lens. Okay. So for the above lens, the source is D naught by 2 below actually. So it will form the real image, which is inverted above, right?
Yes, sir.
So this will form image like this. And this will form image like this. But I'm showing it as a one single. That's why I'm using directly the formula. This is easy to derive. So what is D actually? D is D naught U plus V by U, which is 1 plus V by U, which is magnification formula, right?
Yes, sir.
In value, because V and U, I'm taking everything value. So M is the magnification. And yeah, you can get from there. And once we have the D, okay, once you have the D, as usual, just call this separation, this is U, let's say this is L. I'll call it L this time. So what is D here? D will be how much? The YD, okay, let's talk about the YDS equivalent.
Sir, it will be U plus L.
The capital D.
Sir, sir, L minus V.
Correct.
Yeah.
And the small d, okay, I have taken already. This is. In fact, I took the small d directly there. So this is, and once you have this formula, you can solve further. That's the whole idea.
Okay, sir.
The next
So we are
is,
actually forming like an enlarged image of the original source to make
yeah,
two separate sources and finding their like.
yeah, correct. So what will happen in the reality that if you extend this light ray, they will go on the screen and will get superimposed. So they will interfere. So light ray from that upper lens and the lower lens will move in the opposite direction and they will interfere. That's why, because this light ray will further connection like this, right?
Yes, sir. And there will be a certain overlapping region.
Yeah. The fact is that this entire region will be. So I have taken only one. Let's say you can take like this. So in a way, all region will be interfered. So there is no like the blackout region is not here, as we saw in case of Fresnel and LIyods. Okay. Here there is no blackout region. The entire screen is available for the light to reach, right?
Yes, sir.
So light can reach in everywhere.
Okay, sir.
So by cutting, we can make sure that okay, we create two virtual sources which will act as the two coherent source. And using these two coherent source, we can obtain the YDSC. So this is how we proceed basically.
Yeah. So virtual sources.
Are they physical source? Yes or no? No.
Sir, but then the images are real.
Yeah, a virtual source I'm saying. I'm not saying image and object. I mean, we are not talking in the context of ray optics. I'm just talking about the real source and virtual source. Source, I'm not saying image and object.
Okay, sir.
Here,
Sir,
here the real source is S, no? The physical source. You can say, okay, you can think this way. Physical and non-physical. Let's not call virtual. It's like non-physical source, okay?
yes, sir.
So we have
Here, like virtual means just that the light rays are intersecting at that point.
Yeah. So there is nothing physically present there, right?
Yes, sir.
Just stop. Okay. So we'll go for something next. So far, whatever we have solved, in every question, you must have observed that the source and the screen are parallel to each other. So the line joining the sources and the screen are parallel to each other, right?
Yes.
Okay. So the question is, now we are changing the orientation of source. So we have something called the line joining the source and the screen are mutually perpendicular. So this is the unique case. When so how it will look like. So now the source is like this, S1, S2. And your screen is here. Hmm. So to reach the O, what is the path reference? If the source will, if the light will travel from S1 to O, S2 to O, what will be the path reference?
Sir, would it be D minus D by 2? I mean, path difference. Oh,
Hmm.
sir, it would be only D.
It is? How much you said?
Sir, D with respect to O, right, sir?
Yeah, it's a D only, right?
Yes, sir.
It is simply D.
Yes, sir.
Okay. So that is the maximum difference. No? The difference is maximum, isn't it?
Yes, sir. It's not the generalized one.
The difference is you start with the upper limit only. This is the upper limit of difference. Can
Yes,
we get the difference more than that?
no, sir.
So as you go away from the O, the order of difference will decrease or increase.
Sir, it will decrease, sir.
Correct. So as you go away from the O, the order of interference, order of fringe will decrease. That's the first observation that we need to make here. Okay.
Yes, sir.
All right. So the idea is the O is neither maxima nor minima. We cannot say anything about O. You know why? Because the path reference is known to us at O. At O, the delta X is D already, isn't it?
Yes, sir.
So what will happen at O? D will decide. So let's say if I take D equals to 4 lambda, then the O will become maxima.
Yes, sir.
And we can say this is fourth order maxima.
Yes, sir. Yes, sir.
But if I take D equals to 3 lambda by 2,
It will become a minimum.
minimum. And so if I take D equals to 4.25 lambda, it is neither
Yes, sir.
neither maxima nor minimum, because we cannot say anything now. So what will happen at O? D will decide actually. So now here we cannot say zero order maxima or minima or something. No. the D will decide. And it is the value of D will also let us know that which order of maxima or minima we are going to witness. So if this is 3 lambda by 2, this is like 3 times half wavelength. So this is like 2n minus 1. If you compare with 2n minus 1 lambda by 2, the n is 2, right?
Yes, sir.
So which order?
Second order.
Order minima.
Yes, sir.
So that will lead to the second order minima. The first minima is lambda by 2. The second is lambda by 2 plus lambda. Okay.
Yes, sir.
So the whole idea is what will happen at O, only D can decide. Now we have lost control over what will happen at O, which was something which we were deciding earlier. Okay. And not only that, as we move away from the O, the order will decrease because the path difference will become smaller and smaller, right? So if it is 4
Yes.
lambda now, then 3 lambda will occur above the O, right?
Yes, sir.
Do you realize what I'm saying?
Yes, sir. For a lesser path difference, we have to move away from the
Correct.
O point.
So if I call this as theta, this will be also theta because we know this is very small. This is perpendicular, and this is the path difference. Isn't
Yes,
it?
sir.
So in general, for a point P, so in general, delta x we can write as d cos theta,
Yes, sir.
and definitely the d is very small compared to the capital D. So we can simply ignore. So the 2 points S1 and S2 are so close that you can imagine it's almost there. And therefore, for maxima, you will write from a d cos theta equals to n lambda. Okay, but as you put n, you need to understand that unless we have no clue about the d, we cannot solve the question. We cannot compare it. So if I give you some value of d, let's say if I give d equals to 4 lambda, then we know that the O is the 4th order maxima, then 3rd order is actually above it, isn't it?
Yes, sir.
And this is beautiful. Mathematics will take care of everything because cos function is decreasing function. So higher the order, lesser the angle.
Yes, sir.
So highest order will be closest to the O only. It could be O
Yes.
also. So that's why this is cos theta will take care of all things. So here we don't solve by, you can solve by that way also, but it is always good to write cos theta. And they generally give D in a way that you can, let's say if I give you D equals to 2 lambda, okay, something like this. So they will give you a question which you can solve using this relation. And if you want to write this in terms of yn, then how to write yn? So we can write as cos theta equals to this value, and cos theta we can write as base upon hypotenuse, right?
Yes, sir.
And this we can simplify by writing d upon d1 plus yn square by 2d square binomial.
Yes, sir.
And I will use again the binomial. So generally, depending on the value, we can actually solve or we can use binomial depending on situation. So that's like a difficult thing to understand. We need to solve. All right. Yeah, that's it. So you can solve from here. You can solve actually. This is the better way of solving the question. Whether we need to use approximation or not, depending on what is given in the question. Okay. So accordingly, apply it and get the answer. Okay. So the maximum, minimum, you can keep on writing. The only thing is how to write the path difference. We have seen this. Now we have studied the cutting of lens, but that can also be used in a slightly different way, which is like, what if we cut a lens? So what if we cut a lens and move it longitudinally? So instead of moving up and down, what if we move like this?
Oh,
Like this. And now this is a D naught. And our source is somewhere here. Okay. Let me remove this one. So we call the source as longitudinal source because you can think this way, that light ray will go here, will come here, but the light ray coming from the bottom will go slightly ahead. I mean, these are not much difference, but I'm just exaggerating everything. It's a highly zoomed version. So you can say S2, you can say S1. And then we have somewhere screen. Understood?
yes, sir.
And how we solve it? Because D naught is very small. Okay, so it is like you will treat as a single point only. So it's like the D naught is like the lens is so close that it is as good as one point or one lens. So, but the way of thinking is that uh, instead of thinking as two lens, we assume one lens with two object at separation D naught. It's the same thing, right?
Yes, sir.
The other way of thinking. Okay.
Yes, sir.
So what we do like this? So if we have a lens, I have taught all this thing in array optics because I know this will be helpful in uh, wave optics. So I teach there itself. So it is like you think as two source at a D naught separation. So it will form two images. That's it. Correct.
Yes, sir.
So If we have O1, O2 as two object, it will form ion I2 as two images. Okay.
Yes, sir.
And the relationship is easy to find because for tiny object, because D naught is very small. How will know it's very small? We say if D naught is very small compared to focal length, we call very small. So let's say if F is in centimeter and D naught is in millimeter, so we can treat as this condition. Okay. In such question, the relation is directly written by the formula. D is magnification square D naught. That's it. And the magnification remains the same.
Yes, sir.
So because this entire D is single point and the entire D naught is also 1 point. So we are having 1 point and 1 point here. Object and image. Okay. So this is the relation that we use. And you can use the lens formula again, same fashion. So here D becomes UF by F U minus F. So same thing you will see. The moment we have this D, whatever distance is remaining will become the capital D, right?
Yes, sir.
So this will be your capital D. And the way of solving is similar to this question. Okay, this. Okay. So what is
Yes.
YDSC equivalent? So they will give you the distance between the lens and the screen. Let's call L, and you can call this as P. So these are not, so the gap is negligible. Actually, this is over simplified. You can take center to center. Just take this as. All right, I think. Okay.
Yes, sir.
No. So what is equivalent to the small d will be? I have written already formula. And capital D will be like L minus V.
Yes.
Similar to the previous. And then the highest order maximum will be here and so on. Okay, so we have to check all those.
Yes,
So
sir.
only when you see a question, you will come to know that how to attempt. Right now, it's difficult.
Okay, sir.
Now comes the third variety, which is now slightly difficult. So what if we have a circular screen like a dome shape, maybe? So no matter wherever you turn, you have a screen. Okay. So it could be something like this. So maybe some art gallery may be like this, in which you see there's a wall, and this is the cylindrical room in which you enter and you keep on moving. You can see the art pieces are hanged on the wall, right? So this is the
Yes.
screen now. The screen is here. All right. So now on a circular screen, now the thing is, see, if you look at the situation, earlier we had first screen was like this and second was like this. In the first case, you cannot go here, you cannot reach here, right?
Yes, sir.
And the second case, you can't reach here again. So it's like earlier where you were reaching, now you cannot reach, and vice versa. But in this case, you can reach everywhere, no matter what. So if we have two sources, if we have two sources, and the light is reaching from there, so our screen is here. So if this is D, then this is the path difference, right?
Yes,
So
sir.
the delta x will be D cos theta again. But now there is no constant. The theta can vary from 0 to 2 pi, right? Anywhere. Because screen is all the way everywhere, right? So generally what we do is, because it's a 4-quadrant shape, so we only calculate the answer for each quadrant and rest we replicate. Okay.
Yes, sir.
Now, if the sources are coherent and kept symmetrically, then I can say that this point will be the point of symmetry, right?
Yes, sir.
So this point will always represent maxima.
Yes, sir.
Maxima here also. And we know that these 2 points are a mercy of D, right? Only D can tell you what will happen.
Yes, sir.
So to get a better perspective, let's take some value of D to solve this question. So let's say D is 4 lambda. Then this will also become maxima, luckily.
Yes, sir.
Because the path difference is n lambda. Okay, so now here the path difference is 0. And here the path difference is 4 lambda, right?
Yes, sir.
So as you go from top to the bottom, like from the topmost point to this point, the order will increase, isn't it?
Yes, sir.
So you will get 0 order, then first order, then second order, then third, then fourth order. Okay, so you will get so there are 3 order 1, 2, 3 in between this quadrant, isn't it?
Yes, sir.
So the region of maxima we can get in let's say this is the maxima. Let's like this. Then this is the region of maxima. I'm just taking randomly maxima, and then of course the fourth one is here. So in every quadrant we have 3 maxima, right?
Yes, sir.
So including all the 4 quadrant we have 12 maxima, and the 4 of the vertex, that 16 maxima I can see.
Yes, sir.
3, 3, 3, 3, 12, and then 1, 2, 3, 4. So 12 plus 4 is 16 maxima in total we have. So anyway, for the maxima, So delta x is d cos theta. And this we can write as n lambda. So n equals to 0 is the topmost point, n equals to 4 is the so we can get cos theta equals to n lambda by d. I have written already. So this n will go from 0, 1, 2, 3 up to 4, right?
Yes, sir.
So when n is 4, then d is 4 lambda, so it becomes 1, which is 90 degree. Sorry, 0 degree. So that's like n by 4. Because d is 4 lambda. So if I put it, it becomes, and because cos theta is less than or equals to 1, okay. So that's why n will be 0, 1, 2, 3, 4.
Yes, sir.
Okay, so this is the one question that one should be aware of. The next is, maybe I'll take the last question today.
Okay.
So for that, you need to, I have shared the sheet of YDC wave optics. No? Yes.
Yes, sir.
Open the sheet actually. So search.
Okay, sir.
Yeah, I have shared already. Anyway,
Yes, sir.
so now you can I'll just a minute. Yeah, go to page number 12. Page number 12.
Yes,
Can
sir.
you see? And can you see the question number 2 in the figure shown 3 slits?
E.
Now there is a question of 3 slit problem. Question page number 12 means the 12 of the PDF, the book, not of the like scrolling. 12 of the book.
Yes, sir. Sir, got it, sir. Sir, numericals part 2.
Yeah. Correct.
Okay, sir.
So read about it, think about it, how to proceed, because this is something which I haven't taught. Yeah, but I have taught in another way, but not directly. So we'll see how to attempt question. We have more than 2 slits, 3, 4, 5 like this.
Okay, sir. So,
Okay, so you tried?
sir, I'm just asking if my logic is correct.
Yeah, tell.
Sir, so like according to my calculations, I'm getting d square by d would be the path difference.
Okay.
And like we'll get, and there must be certain path difference for a maximum. I mean, like there must be certain path difference that is n lambda for a maxima to be
Mhm.
obtained at the given point.
Yeah, which point are you talking about?
Sir, the one directly in front of S2, the middle one.
The middle one. Okay, okay. Okay, so to reach
So,
the point, let me give you the process. This process is simple. I'll just tell you. It's a very uh, typical way of solving any or adding many vectors. Like so, you know how to add vectors, right?
yes, sir.
So we have to think about phasors in terms of phasors, and
Okay.
we have to think like which will be ahead of phase and into the phase, like this. So imagine our question is there is three slits, right? One, two, and this is the third one. So this is S1, which is S1. This is S3. Okay. And you want answer where? You want answer in front of second one, right?
Yes, sir.
Fair enough. So who can reach fastest here? S2 only, right? Because S2 has to travel.
Yes, sir.
Now the question is, if I write the phase difference between the S2 and S3, what will be that?
Sir, S2 and S3, it would be d sine theta.
Yeah, I think this angle, if I take as theta. Okay.
Yes, sir.
So this is also theta. This is 90. This is also theta. So this is of course this is D and D given. So D is under, right?
Yes,
So the whole idea is if the amplitude of S2 I take as a reference. So source S2 is the reference. And if the amplitude of wave of source S2 is like this, the path difference between S2 and S1. S2 and S1. So who is leading? S1 is leading,
sir.
right?
Yes, sir.
S1 is leading, isn't it? Because the one who is traveling more will leave first in the time frame to
Yes,
reach at the same time. So it is leading, and it is leading by a phase difference of let's say 1 and 2, and phase difference of 2 and 3. Both will be same.
yes, sir.
2 pi by lambda into d sin theta.
Yes, sir.
Okay. So this is going to be same for this difference and this difference as well, right?
Yes, sir.
Okay. So let's call this as phi to make it easy. Just a minute. Okay. Yeah. So the idea is other will lead. Okay. So how we write the answer? So we have to start from, if I take the middle one, then the other will be like this. I think just a minute, let me read the question first. Yeah, just a minute. Because each slit produces same intensity eye on the screen, which means all will have the same amplitude as well.
Yes, sir.
Yeah. So I think we can draw like this. So if this is S2, what is where is S1?
Sir, above.
And where is S3 then?
Sir, it would be the same, right, sir?
Yeah, right. So it is like you are trying to add A and 2A, isn't it?
Yes, sir.
So the answer becomes it's a 2 vector, A vector and 2A vector. So what is the resultant vector? A square plus 4A square plus 2A square, no, 4A square, right? 2AB into cos phi. So it turns out to be 5 plus 4 cos phi into A square, right?
Yes, sir.
So we can say the resultant intensity is 5 plus 4 cos phi I naught or I simply, right?
Yes, sir.
What is given in the question? That IR is free I. You can read, right?
Yes, sir.
IR is CI. Am I correct?
Yes, sir.
So 1 implies 5 plus 4 cos phi is 3, right?
Yes, sir.
Oh, I'm solving here only. And then cos phi is how much? Minus 2 by 4, correct?
Yes, sir.
Minus half.
Yes, sir.
And cos phi is minus half, so phi is how much?
5
Pi
would
minus
be,
pi by 6. 5 pi by 6. No?
yes, sir, 150 degree.
So we cannot 5 pi by 6. Like pi by 6, sorry, pi by 3. Cos 60 is half. No?
Oh, right. Yes, sir.
So pi minus pi by 3 is 2 pi by 3. Pi minus pi by 3. 2 pi by 3. Which is 2 pi by lambda d sin theta. So basically d sin theta turns out to be lambda by 3. So sin theta is and sin theta we can write, right? In terms of d and capital D. Which
Yes,
is
sir.
d by d only, right? D by d.
Yes, sir.
Right? This is the answer. Yeah. Sin theta is tan theta, the d by d. Fine. So let's say so lambda becomes Okay, I think we need to take the approximation exactly by taking the difference. What is the path difference? The path difference here is just a minute. Path difference is just a minute. D square plus D square minus D. We have to solve exactly the difference, right? Because the point is in front of the slit, so we cannot take this sin theta formula. The rest is fine. The way we have derived is fine. So we cannot take this as delta x. We will calculate the delta x. So this will become how much? Yes. Delta x. So delta x is how much? Lambda by 3, right? That is what you can add. And from here you can get d1 plus d square by 2d square minus d, which is like d square by 2d actually. This will come. That's why we are getting the wrong ones. Anyway. So now delta x is how much? Lambda by 3?
Yes, sir.
So lambda is how much? And if you compare with the formula which they have given, n is
3.
Yeah. So when we have the point in front of slit, we have to take the actual difference and then take the approximation. Don't use d sin theta. That will give you the erroneous answer.
Okay, sir.
So I think similarly, there's a question number 3 also you can attempt and you can solve. So start solving. You will be able to solve most part of it. Next lecture, I will keep it as a doubt lecture, and then I'll start something called interference through thin film interference. So there's something called thin film interference, which I haven't taken. It will be taken care in the next lecture. Okay.
Okay, sir. Yes, sir.
All right. Bye and take care.
Bye, sir. Thank you, sir. Sir, and also
Yeah.
the 2 PPTs.
Yeah. I'll share it. Don't worry.
Okay.